Undercurrent is a common protection element in the motor protection relay. This P40 enhanced IED also provides an undercurrent element per phase group for alarm and trip. The element responds to per phase current. An alarm will occur if the magnitude of any phase current falls below the undercurrent alarm pickup level for the time specified by the undercurrent alarm delay. Furthermore, a trip will occur if the magnitude of any phase current falls below the undercurrent trip pickup level from the time specified by the undercurrent trip delay.
Undercurrent setting is a little different with other common elements. It has a separate settings for both the trip and also alarm. So there's no setting for the function which has the 4 options as other element. Only 2 options is trip, config, or alarm and config. And there's a inhibit at the bottom for the both elements. In the beginning, there's a start block delay, and this setting allows the connected load to build up to a certain level before the undercurrent element trips or alarm. Trip set or alarm set defines the threshold to trip or alarm, and these pickup levels should be set lower than the lowest feeder loading current during normal operation. Then the delay and the T reset are the same as the most current element used for the delay and for the dropout. In the logic diagram of undercurrent, we will show how the trip element works. The alarm has the same principle. The inputs are the 3 individual phase current compared with this trip set, then pass through an OR gate to the next AND gate. The red-colored CB close is the status of the breaker. Undercurrent requires a breaker closed condition to activate this element. Once the breaker is closed, the element will be blocked for a period of time defined by the setting start block delay. And after that, any phase current IA, IB, or IC is below the threshold that will output the operand. I greater than 1 trip, PKP or OP in UK English. In the US English, they are undercurrent, UNDER, CUR, in one word, then trip, PKP, and trip, OP.
For the thermal overload protection, thermal time characteristic is based on the equation I²RT. The device provides 2 characteristics for thermal overload protection, a single time constant characteristic and dual time constant characteristic. This can be selected according to the application. The single time constant characteristic is used to protect cables, dry type transformer, and capacitor banks. The dual time constant characteristics is used to protect equipment such as oil-filled transformer with natural air cooling.
In the thermal overload protection, there are 2 options under characteristic, single and dual. When the single time constant is chosen, the heat and the cooling time constant has only 1 setting for each. And the trip time can be calculated with the equation. When the dual characteristic is chosen, then the heating and cooling constant, each one has 2 settings. This characteristic is also given by the equation in the manual. So how to choose the time constant for different applications? There's a detailed information in the instruction manual in the thermal overload setting guideline session.
There are two undervoltage elements which will be covered in this session: phase undervoltage and positive sequence undervoltage. The positive sequence undervoltage used Fortescue equation to calculate the positive sequence voltage at the input. So it's necessary to review how the positive sequence voltage are calculated for Y and delta connected VTs.
In the phase undervoltage, the function setting has the same as the current element, that's trip alarm, latched alarm, and configurable. The measurement mode has the phase-to-phase or phase-to-neutral two options. When the VT is set to delta, then the phase-to-phase mode should be chosen. And voltage set is the pickup level. It's in the multiple of the VT, and this is the nominal VT depends on the measurement mode. Minimum voltage level, that's the supervision voltage level. Only when the input voltage are higher than this value, the signal are considered valid. Operate mode can be set to any phase, two-phase, or three-phase. When changing from any phase to three-phase, the three individual phases need to pass an OR gate, now changed into an AND gate. The curve can be set into the IDMT or the DT, plus 4 user curves, which was introduced in the 103 modules. The setting is under the device. When DT is set, the TMS change into the time delay, it becomes a definite time delay. And if the change the DT into the IDMT, then this time delay changed into the TMS. This is the multiplier. The curve can be calculated by using the undervoltage IDMT equation. Next, positive sequence undervoltage. It's similar like the phase undervoltage. The only difference is that the input is not from the VT, but it's a calculated positive sequence V1. And this V1 was introduced in the Fortescue equation. So all the rest settings are the same as the phase undervoltage. It has the curve setting of the DT and IDMT, just has no user curve. And also it has the minimum supervision voltage and a plus inhibit.
In the overvoltage element session, we'll cover the 5 elements: phase overvoltage, residual overvoltage, which including measured and derived, positive sequence overvoltage, and negative sequence overvoltage. In the previous session of the undervoltage element, we reviewed the Fortescue equations of the positive sequence voltage calculation, and now it's time to review the negative sequence voltage calculation for the Y and delta VT connections.
The phase overvoltage is the opposite of the phase undervoltage. They share most of the common settings like function, measurement mode, two options, and also the operate mode, 3 options, single phase to 3-phase. And they have the set of the voltage, that's for the pickup level. Also have the curves. The only difference is the curve calculation IDMT are different. They're using different equations. There's another minor difference is that there's no supervision level, minimum supervision level for the phase over voltage. In the next, residual over voltage, there are 2 ways. M stands for measured and D stands for derived. So the measured over voltage, the input is from the auxiliary VT, the input, and its English, US English name is auxiliary over voltage. And for the derived over voltage, that's the internally calculated neutral voltage, and its English name is neutral over voltage. And this neutral voltage is calculated Vn by using the Fortescue equations, and other settings are the same as the phase over voltage. And next, the positive sequence over voltage. This is the input coming from the calculated positive sequence over voltage. And we can see this V1 stands for the positive sequence over voltage. And we have this common settings function and also the curves. You can choose to be IDMT or the DT. And the last is the negative sequence over voltage. This is the input coming from the calculated negative sequence voltage. And we can see this is the V2, that stands for the negative sequence voltage, and it has the setting, but for this one it has only the definite time delay. There's no IDMT. So that concludes all these voltage elements. There's a totally 2 under voltage and 6 over voltage. Then the 2 residual over voltage has 2 different inputs for the measured and it derived, but the output operands are the same. And all this detailed information can be found in the instruction manual.
Power protection is usually used for the generator protection. P40 and gel enhanced P14D has overpower and underpower protections can be used for protecting small distributed generator, typically less than 2 megawatts. Power element is only available for the P14DL Cortec autocode IED.
There are 2 distinct conditions for the overpower forward and the reverse. A forward overpower condition occurs when the system load becomes excessive. Generally, the forward power protection element would be set above the maximum power rating. And the reverse overpower conditions occurs when the generator prime mover fails, and when this happens, the power system may supply power to the generator, causing it to motor. This reverse of power flow usually happens due to loss of prime mover. Depends on the types of the prime mover, the reverse overpower can be set less than 50% of the motoring power. The typical levels of motoring power for various types of the generating plant can be found in the instruction manual. And the mode can be set active to be or to be in reactive. The reactive power element and usually to be used to detect loss of excitation. In the under power session, this can be programmed as the forward, reverse, and most common setting is application for this under power is a low forward power protection for various applications like interlocking of non-urgent tripping and loss of load protections. The setting guidelines can be found in the instruction manual.
P40 RGL enhanced IED has three frequency elements: under frequency, over frequency, and frequency rate of change. ROCOF. These elements can be used for the load shedding to balance the generation and the load. Each element has 9 levels of protection. ROCOF is only available for the P14DL Cortex order-code IED.
The under frequency function can be set trip, alarm, latched alarm, and configurable, same as the overcurrent element. Then the frequency set is the pickup level, which should be set below the nominal frequency, either below 50 Hz or 60 Hz. Then there's a time delay and reset delay for this element. VT input is where you select the input voltage signal. Could be from the bus VT, you can choose the 3 VT, or you can choose the fourth VT, it's the wired on the auxiliary VT input. And this element is supervised by the minimum voltage and current input. That's the setting V minimum and I minimum. And last one is the inhibit settings to block this function. The next over frequency is similar like under frequency, just all the settings are opposite. So we can see that the VT inputs can be set to the 3 VT or the 4th VT, and the frequency set is the pickup level. This time should be higher than the nominal frequency, either higher than 50 or 60 Hz. Then there's a time delay for the trip and the reset time delay. And also, so this is supervised only by the voltage minimum. There's no current supervision for this over frequency element. And last, rate of change of the frequency ROCOF. So this one has more settings. So first we see this the function can be choose trip alarm. Then this has a direction setting. So you can choose positive or negative. This determines whether the setting is in a falling or rising frequency direction. Then the set is in the unit of hertz per second. So that's the rate of how quickly this change frequency. So this by default 2 hertz per second. And then there's a time delay for the trip. And this is supervised by a frequency range from 45 to 65 hertz. This can be changed. That's the supervision. Again, it has the VT input options. You can choose 3 VT or the auxiliary VT. And last, this is supervised also by the minimum voltage level and current level. So that's all the settings for the frequency rate of change. And that concludes all this frequency elements session.
Now let's recap what we have learned in this training module. First, we introduced the phase overcurrent elements, including phase TOC, IOC, directional OC. We used phase IOC explained the common settings from function to inhibit. In the logic diagram, we introduced each logic input and output operands in both UK English and US English. The main difference between the IOC and TOC is the DT delay changed into the IDMT delay. This applies to all the other kind of IOC and TOC elements. The phase direction OC has no output operands. It internally controls the phase IOC and TOC if their directional settings is set to forward or reverse. In the earth fault overcurrent elements, we introduced EF1 and EF2 IOC, TOC, and directional OC, and REF. Also, their corresponding US English names, ground OC for EF1 and neutral OC for EF2. So to simplify, the relationship is G1 and 2, which means the ground OC is for EF1 and neutral OC is for EF2. Their relevant directional overcurrent element controls the corresponding IOC and TOC directional settings. It's the same as the phase overcurrent element. And don't forget, there is one positive sequence restraint key factor in the EF2 IOC or neutral IOC in US English. Switch onto fault SOTF logic uses breaker status and command of closing the breaker. And for the negative sequence overcurrent elements, we introduce the negative sequence TOC, IOC, directional OC, plus the broken conductor. We review the Fortescue equations first. The inputs are all using the calculated negative sequence current. For negative sequence IOC, there is a positive sequence restraint key factor like 50M, but with different values. Broken conductor uses the ratio of the negative sequence over positive sequence current. In the undercurrent element, we learned this element is working only when the circuit breaker is closed. It has separate trip and alarm functions, not under one function setting as other elements. Thermal overload has single and dual time constant characteristics. In the voltage element session, we introduced the phase, under voltage or voltage, and positive sequence under voltage and over voltage, negative sequence over voltage, and residual over voltage. There are two types of residual over voltage measured and derived. In the power element, we talk about the over power and under power. And finally, in the frequency element, we introduced under frequency, over frequency, and frequency rate of change. And remember that power element and the frequency rate of change, they are only available for the P40DL Cortex autocode IED, not available for the P40DB IED. Protection elements are the most important part of the P40AE enhanced IED. For the more detailed information of each element, please refer to the instruction manual. And that concludes this training session for the P40AE enhanced 104 protection controls training module. Thanks for watching.